we wanted to compute this part. Can you see delta loss? Can you see my pointer?
Yes.
Yes, sir.
Okay,
Yes,
very
sir.
good.
It's clear.
So delta loss with respect to delta Wij. So because this is the part we want to compute. So what we do using chain rule, delta loss with respect to delta AIL. What is AIL? If AIL is a node AI at the layer L. So you have the input here, it will come input from here and so on. Okay? Multiply it into delta AI at level L into delta ZIL into delta ZIL delta WIGL. No doubt, right? Now what we know it here, maybe I don't know, can I see it here? AIL equal to function of ZIL equal to what? Function of summation over
Excuse me, sir.
Yeah.
Sir, the screen is not maximized.
Huh?
The screen is not maximized, sir.
Yes,
Your
sir.
tab
It's
is
spotlight.
very small.
Oh, I should spotlight. Yeah, I should spotlight myself. Spotlighting myself. Okay.
Yes, sir.
Okay. So now this one is WL, then AJL1 plus BIL. Okay. So now what we have to do? Let's say this one we said key. You assume this one equal to delta I. Now this one we already computed earlier, so I don't want to compute again. This will be the third time. WIL into 1 minus AIL. So this one basically corresponds this part. Okay. Okay. Now what is next? Next is this one. We have to compute this part. How do we compute this part? What is ZIL? ZIL is here. ZIL equal to summation over WIJL AJL minus 1 plus BIL. Now you take a derivative ZIL with respect to Wij with L. So what I said, this is a summation, means there will be a different parts. Wi is fixed, so J1, J2, J3 similarly this one, but with respect to J particular value of J. So then rest of the thing will be 0. Only one value will be there, that is Wij, AJL. This is only the variable. Rest will be the constant. This one also will be the constant. So therefore this will be value will be AJL1. So therefore, what you will get it at the end of the day? So you will get here multiplied into AJL1. Okay. This one I told at least twice. Okay. Now focus is actually for today's class is only for this part. Okay. Delta IL, that is the part I should talk here. Now what is this? This one is nothing but you see here. Okay. So maybe what I can do it. This one, please remember what is this. So what I do it, or I can remove this part. Only I remember delta AIL delta ZIL equal to AIL into 1 minus AIL. Okay. So rest of the thing I can just remove it. Okay. So what I have to do? I have to compute delta loss with delta I L. That was the first part here. First part was here, then this one is the second part, and last part was there. So now I am focusing on this part. What we did it, we considered this is delta I L. That is, we did it. Now what is this one? What I do for computing this one, what I do, I will start from the last node. So let's say this is the last node. So then there will be a node here. There will be a node here. There will be a node here, and so on. So this node is node A and level capital L. So if you replace this one for all values of I and all level, so this will come. What I have to do it now? We compute delta loss. We compute to delta L last level. Okay. So loss with respect to last level will be delta M with respect to what is the loss function? Loss is y minus y cap square. And please remember, last value here is actually here value at last output will be a L. So what you can do it, you can put the value delta A L equal to 1 A L. So this is the output of from the last node. Okay. So then you should take the derivative. So what will come? This is square. So this will be 2 into 1 y minus a l with respect to l. So it will be minus. So if you take out here, so this will be how much? Okay. So this will be 2 into y minus a l into minus 1. Okay. So this will be 2 into al minus y. So do you agree with that? So therefore, what we can write it? A we got it. Okay. So therefore, delta with respect to L. Okay. Last node. This is equal to 2 into A y L. Okay. So this is with respect to last node. This is nothing but delta loss with respect to delta A I L. Is it okay? Okay.
Yes, sir.
So next, what you have to do? We have computed loss with respect to the last node. Now what you do? You compute the derivative with respect to the intermediate node. Let's say this is the node at the level L. So L is nothing but here level is L minus 1. Okay. So what you do it? We consider this level is L. So therefore this level will be L plus 1. It is the same thing, right? So what we do it? We compute delta loss with respect to delta A I with node L. That is the thing we need to compute, right? Delta loss with respect to del loss with respect to delta A I L, right? That is okay. I somewhere so delta I with respect to L equal to delta loss into delta I with respect to L. Okay, that is we have to compute it. Again, we apply the chain rule. So delta loss with respect to delta what? A I L plus 1. Whatever the we know that first, because this is given with respect to, first we compute and then we apply the chain rule. This one into delta AI L plus 1 delta Zi L plus 1 into delta Zi L plus 1 with respect to delta AI L. You need to understand this part. Okay, maybe I can, everything I can remove here. So cleaning the board is a good part. Okay. So delta loss with respect to delta AI L. So that is we need to compute. Okay. What we can do it using chain rule, I can write delta loss with respect to delta I L plus 1. When I computing this one, before that I should know the value of just previous node level. And then delta AI L plus delta L plus 1 with respect to I L plus 1, that means within this node only. And then finally this node. Now what you do it, when you computing Lth node, we should know the value of L plus 1. So in this scenario, if you compute L minus 1, we know this. This is already known. What is that value? So in this example, this is 8 delta I L. So this is delta L only, because this is the last node. Multiplied. This is already we computed. That is why I said we should remember delta AIL with respect to delta ZIL, AIL into 1 minus AL. So now if you put plus 1, this will be plus 1, this will be plus 1, this will be plus 1. So here we can write AIL plus 1 into, okay. So this is AIL plus 1 into 1 minus AIL plus 1. Okay. Now left over is this part. Okay, can I use different color? I don't think you can see it here. Okay. So what is this ZIL? That we computed, we know. AIL, what is the ZIL? We know. So ZIL, we know. ZIL is equal to this part, right? If we remove only this part, is nothing but this part. So therefore, ZIL we can write here L plus 1, right? Yeah. That is we need to compute. ZIL equal to summation over W. If it is L here, it is L. So therefore, W Ij L plus 1 A. You see L minus 1. So therefore, L plus 1 it should be L plus B I L plus 1. Now what you have to do? You have to compute delta Zi L plus 1 with respect to, I did wrong anything. Anything wrong? Delta AIL. That is, we need to compute here this part. So now similarly, what will happen? That all will be the constant, only the term will fix it. This is AI. This is it should be AI. Okay. So only the term will consist along with this value will be there, rest will be 0. So therefore, if you take the derivative with this one, let's say this is x, something into x. So therefore, so it will be the value of Wij L plus 1. Okay. So therefore, here you write it the value. I think now I can write it. Here I write it Wij L. Is it okay? L plus 1. Okay. So now what we found it here, So this is the value for delta loss A I at which level? L minus 1 level if it is L. Okay. So therefore, in general, what we can write it? We can write whatever the value here, whatever we are computing here. So let's say what we write? It is L minus 1 if it is L. So now other way around, what we can write? If it is computing L, we can put here L plus 1. There is something problem, I think. Not function. No. Yeah. Is it okay? You have to respond.
Yes, sir. Yes.
I am trying to share the slide. I think slide is with you. Somehow it is not coming again. OneDrive. So you can see the slide.
No, sir.
But you download and see because it is creating problem. So and you check whether, and then if you have a question you can ask in which part you are not understanding. Oh, I don't know, it is not opening somehow. So everything is not happening in the right way. It's upload from my computer, okay.
Sir.
Yes.
Sir, can you summarize from multi-perceptron why we use this gradient descent once
Morning talk, whatever you are saying, morning part.
Yes, not sir, not morning part I'm just saying sir, please summarize all that thing from multi-layer network.
See, multi-layer network, we have multiple perceptron. Okay.
Yes, sir. Yes.
So multiple perceptron, then we have to fix the weights of each incoming weights. You have to fix the weight of the incoming signal or whatever you say, that is Wij. Now problem is because we have a different type of layer. So in hidden layer, a particular node, how much it contribute, it is really difficult to identify from only the loss from the output node. So therefore, we cannot use the same technique we used for single perceptron. So therefore, we have to use a loss function. So that is a different loss function. Earlier, we did not take the square of this one. So now we are taking the square of the original value minus predicted value. So what is the advantage of that? Now it is like a very nice quadratic function. Okay. Now, if you in the morning class you have seen that if it is a quadratic function, and for I have shown for a single variable function. So what is the advantage that single variable, if it is there and problem is minimization, then there is a standard approach to use the gradient descent approach. And what is the advantage of gradient descent approach? As I said it with simple example. So that formula will come, that is something if you want to update the new values, that is old value minus lambda into delta E by delta Wij. Why delta We by delta Ij is nothing but the gradient at that particular point. So simply if you say y equal to x square function, that is like hyperbola, right? So in that case, in a particular way, so it has, let's say, left side and right side. So essentially at each point you compute the what is called is gradient, and you go much closer to the original point for which it will get the minimum value. And I clearly have shown you that key always, whether it is in the gradient is positive or negative, the same formula will be used and you can reach to the that is the minimum points. Therefore, we use the gradient descent for this approach. Okay, and rest of the thing, whatever the formulation, it is like a simple derivative we use. Similarly, we have shown for the Wij. There is another variable that is Bi. Okay, so therefore you have to use the same tricks for Bil, and then you have to come up with those values. The advantage of BIL is that rest of the summation part will be always 0, only BIL, and that is the BIL with BIL will be 1. So that is why we use the gradient descent for getting the weight of the each individual signal or whatever is input of the each internal node also. Okay.
Yes, sir.
So, in concluding remark here, so we have learned quite number of classification techniques. Okay, one major classification technique I am not covering in this class is something is called support vector machine, because its time is really going through fast. So I have to complete some other portion of the data mining. Okay, so therefore I will clearly jump in tomorrow's class on, there is something called what is called is the ensemble of classifier. Okay, in tomorrow's class we talk about the ensemble of classifier, and then maybe by Friday or maybe the next week I'll talk on classification technique, sorry, clustering technique. Okay, so support vector machine this time I am not going to cover, because this time I introduced that is ANN. Generally, I do not cover this ANN because you will have a course on deep learning. We are expecting there will be a course on deep learning, so there also it will be introduction. So having said that, we'll complete. We will proceed in the next class. Is something called is the. It is obviously advanced topic. Also, this is called the ensemble of classifier. Okay.